factoring two-term polynomials, and more specifically looking at the sum and difference of two squares. So the first thing that jumps out to me when I'm factoring these kind of problems is they're two terms. And so when I'm given that kind of problem, I'm thinking, okay, I'm thinking special factoring formulas because they are two terms. Now, the other thing that I'll glance at when they're two terms is right away I glance at the power. The power is a 2, I'm thinking, okay, squares. So you want to recognize that kind of thing. The sum and difference of two squares, the sum of two squares is actually prime. Anytime you recognize that you're dealing with two terms that are the sum of two squares, you cannot factor those over the integer. It's impossible. So whenever you identify that a squared plus b squared, you recognize it's prime and you say it's prime. Difference of two squares actually is factorable, and it factors down to two binomial conjugates that are the same binomial except for the middle sign switch, so that when you remultiply, the middle term wipes out and you get a minus in the back. And so these end up being the difference of two squares. So I look at this, I picked 6 problems to summarize this. And so we're going to run through these. And just before we run through these, let's actually look over here at the list 2 of squares. It helps to recognize that these numbers, the perfect square numbers, I would say maybe up through 12. That's right about what you usually see in the homework problems and that kind of thing. So get used to knowing, or I would say know those. 1 through 12 squared, the perfect squares of those numbers. So I glance at number 1 and I know 4 is a perfect square. Plus x times x is x squared, so I know this one's prime right off the bat because it's the sum of two squares, does not factor. This one, number 2, also prime for the same reasons. The reason being here, this is really 2 times 2 or 2 squared. This is p squared or p times p, so 2p quantity squared is this term. And this is 9 times 9, so I know that's the sum of two squares. The whole term in itself has to be a perfect square, even the number parts if there's more than one part to it. And that one is prime. This next one, I'm looking at this, I'm like, wait a minute, 300 is not a perfect square, 3 isn't, so this doesn't really seem like it would be a sum of two squares. But I see that square there in a plus sign, but you always have to remember that golden rule of factoring. Take out the GCF first. So when I take that 3 out, I'm left with m squared plus 100. That's actually my final answer. Why I know it's my final answer? I cannot factor m squared plus 100 any further because that is prime. This is the sum of two squares. This part of the problem is the sum of two squares. And a common mistake I'll see is someone will write prime for this for an answer. It's not. You did do some factoring. You factored out a 3. Then you recognize this is not factorable any further, so that is factored though. 3 times m squared plus 100 would be the complete factored form of 3m squared plus 300. The next one, this one I noticed the minus, but the powers are telling me, I'm thinking difference of two squares. So, and it is. This is x times x. This is 4y times 4y, right, in the back. So I would actually plus minus, right, my binomial times binomial. I know that they're conjugates of each other. And then I know what's being squared in the front goes in the front. What's being squared in the back, which is a 4 and a y, goes in the back. 4 and a y. And that's it. All right, number 5. We have 2 more examples here. I'm looking at this one, same deal. I'm looking for golden rule of factoring is always a GCF because I recognize it's a square, it's a minus. I'm thinking difference two squares. That's not a perfect square number either, is that. But you always have to, golden rule of factoring, take out that GCF. Now I'm left with a w squared minus 25. And hey, now this thing is the difference of two squares. It does factor further. So I'm going to take out the 5 and I'll be left with w goes in front. The 5 just tags along, it is a factor. W is being squared in front, so it goes in the front. Plus minus, 5 is being squared in the back, it goes in the back. Factor it completely. So always remember that GCF first. Number 6, and the final type of example I put on here is, this is the difference two squares, because that's 3 and an m, and this is 1 and 1. 1 is a perfect square, perfect cube. So I'm going to end up jumping to my plus minus. 3m goes in the front and both of these. All right. And and then 1 goes in the back. 1 times -1 is -1. And there's my factored version of it.